Tonight, I thought we would talk a little bit about data types and why, when you're designing tables and dealing with data, when you look at the tables that you're having to query because you've been asked to deliver some data for some business intelligence, that knowing and understanding data types might help you understand what could be happening with your queries and give you some insight into some performance considerations. So what we're really talking about initially is, should we oversize our data types? Yes or no? Yay or nay on that? Does a last name column need to be varchar 256? Do we really need a free text column into which we could type anything? Or in a user application like in a web browser, we're going to let a customer type whatever they want. Is that even a good decision that kind of forces us to choose something like invarchar max as a data type? If we are going to have a column that's going to be a number, should we use big int by default because that gives us all the numbers we think we're ever going to need? Is that a good idea? That's the kind of thing that we're going to be talking about, and talking about the kind of impact that that could have for your applications. So one of the things that you might not be aware of is that oversizing your columns can actually cause large memory grants. So what does that even mean? What is a large memory grant? What is a memory grant? When you create a query and you're typing away in Management Studio and you hit F5 or execute, the system submits the query to SQL Server. And one of the first things it does is a calculation for how much memory is this particular query going to need. SQL Server then takes, one of the things SQL Server takes into account in that regard is to look at the data types that are involved with the tables that are being queried. So if you have a bunch of data types that are very large, like invarchar 256 or 512 or max, and you're joining several of those together and they all have large data types, SQL Server is going to estimate a very large amount of memory is needed to run this query. And that is the memory grant that SQL Server thinks it needs to give to this query in order for it to run. And that memory has to be there before the query can even get started. So if you have 128 gigs of RAM allocated for your SQL Server, and you have a query that is getting a memory grant of 10 gig, that's almost 10% of the RAM just for that one query. And if you have 5 or 6 queries like that are being submitted to the engine at one time, that's half your memory. That seemed like a crazy example that would never really happen, but I've seen that. And I've seen larger memory grants, like in the 20 or 30 gig range for a single query in a box that only had 128 gig of RAM. So if a query needs 30 gig to get started and you only have 128 to give it, you can only run 4 queries at a time. And when that 5th query wants to run and all the RAM is being used, the query can't run. It just sits there and the application grinds to a halt. The client starts hitting F5 on their keyboard because nothing is happening, and that just submits more and more and more queries. And it creates a storm where there's a log jam of queries waiting to get memory. And pretty soon the customer is going to be on the phone to support because the application doesn't work. And the DBA or whoever happens to be doing production support is going to have to try to figure out what's going on. And so oversized columns can contribute or do contribute to this problem of large memory grants, and you essentially run the SQL Server out of memory. Oversized columns also can hurt the ability to properly index. And here's what I mean by that. So you only have 900 bytes for a clustered index. So the clustered index in SQL Server is the key column, the one or more columns that are actually ordering what we call the lower leaf levels of the table. It's the ordered table. You only get 900 bytes. So if you're doing something like using large strings and you're using several columns of large strings as your clustered index, you might be bumping up against this limit. The other issue that you would have, which I ran into, is you only have 1,700 bytes for a non-clustered index. So let's say you have a table with 10 or 15 columns in it that are sized for varchar or invarchar 256 or 512, because somebody thought, well, we don't really know what kind of data is going to go in here, how big it's going to be, how long it's going to be. So let's just set it high, and that way we'll always be covered. If people start, typing out and running queries, sometimes custom queries against those columns, and without any kind of clustered, without any kind of non-clustered index, that could be really slow. So a person like me, or a data engineer, or someone just responsible at your business for performance, looks at the situation, they look at the query, and they think, what if we created an index that included most of these columns that people are querying on? And so they tried that. They crafted an index, and they stuffed 5 or 6 columns into this index definition, and they run it, and they get a warning. SQL Server let them make the index, but also what happened is that they got a error message or a warning message saying, hey, this index is over 1,700 bytes. Some queries like inserts might not work. And so you don't want to be up against that limit simply because you have a bunch of oversized columns that you need to get into an index. I've seen lots of scenarios where I have looked at columns that were sized very large, and I would do a max length. I would get the length and the max for that particular column, and it would turn out that the maximum length in an invarchar 512 was 20 characters. You really need an invarchar 512 if the largest thing you're storing after 10 or 15 years is 20 characters? I would say not. You should probably downsize it. And I ran into a lot of tables that are set up that way. Tables that have been created using an object relational mapper or an ORM to help do database creation when it wasn't used correctly, created a database that had tables as full of invarchar max. And that's also an issue that we're going to talk about later. For SQL Server 2014 and earlier, all versions supported 900 bytes for all index types. That was the max that you could do. So I'm getting this information from a Microsoft Learn article that I've created a bit.ly link for there on the screen, so that I'm not just making this stuff up. You can go check that I actually know what I'm talking about. Here's where I mentioned invarchar max earlier. Here's where another way in which it can hurt you is that it can't be in the key of an index. So if someone's decided, well, we don't really know how big this, how big the text is going to be, how much is someone going to type into this field, so we're just going to let them type as much as they want, essentially. We'll just make it max. And then those fields are queried very frequently. You run into a problem because you can't include them in the key for an index, which means they're not they can't be used for any kind of ordered search. They have to be essentially appended to an ordered search index in the include list. So invarchar max hurts in that way as well. And oversizing columns hurts you in that way as well. Invarchar and inchar, those Unicode, non-standard, non-English lettering systems, when you're using invarchar and inchar, they use 2 bytes of storage for every character. So if you're not storing a foreign language in your application, then there's no need to design the database to hold non-English characters. You're just making the database larger than it has to be. And you think, well, what's 2 bytes of storage per character? Well, I don't know. Think about the fact that you have, 500, maybe a 500 gigabyte or a terabyte database. And if you have a bunch of inchar or invarchar and across 30, 40, 50, 100 tables, and you don't need something other than the English language across that many tables and columns, those 2 bytes adds up to a significant amount of storage that you're essentially just wasting. That kind of decision makes for larger tables, and those larger bloated tables actually means that your backups are going to be larger. And you think, well, why do I care about that? Well, you might not, but your company certainly does, and here's why. This larger backups means longer backup times, meaning larger maintenance windows that are necessary to actually run the backup. When those backups are running, especially if you're in cloud, you're using up available IOPS for your storage that could be used for your application. And so the length of time in which that backup runs adds to the I/O workload of that particular SQL server. And if it happens to spill over into a busy time for your application, you could actually cause problems for your application performance simply because you're taking backups. And those backups are running long because your database is stuffed full of oversized columns. Larger backups also means more storage. And again, you might think, was it storage cheap? Well, yes, compared to, 1950 or even 1990 or 2000, but still not free. And especially in the cloud, you need to store those backups. Your company may store 90 days. They may store 180 days worth of backups to make sure that they can recover from something. And storing that many weeks and months of backups that are larger than they have to be just causes your company to spend more money than they would have if tables and columns had been sized properly in the first place. Larger backups also means longer restore times. If a database is 2 terabytes and you're using compression in SQL Server, you can often get a backup that's half the size of the actual database. So let's say you have a 2 terabyte database, the full backup is a terabyte. It takes a lot longer to restore a 1 terabyte database than it does 500 gig database or a 500 gig backup. So if your database is sized properly, if your columns are sized properly, your tables will be smaller and they will be backed up faster. They will take up less space, and you can actually restore, or your company, someone at your company can actually restore quicker. And that's important because when there's some kind of a delete or a mistake with data that's been made and you need to recover, or someone needs to recover, the customer may often be waiting for that recovery to actually occur so that they can go on with what they would normally do with your application. And so that's why it's important to think about longer restore times that result from larger than necessary data types sitting in your database. Poor data types and data type choices can also cause or do cause implicit conversions. So if you have parameters in your stored procedures as an example, let's say you have a parameter for first name and last name, and you're querying a person's table. Your parameter for first and last name in the stored procedure, maybe you've typed it as varchar or in varchar, 50. Last name is in varchar 100. And when that parameter gets passed into the stored procedure with the value, it's being compared to a column that is varchar. Well, SQL Server then has to do SQL Server then has to do a conversion up to the highest data type in order to compare the parameter to the value that's actually sitting in the database. The same thing happens with like an int and a big int. There has to be a conversion there in order for SQL Server to do a join or compare parameters. And so when you type, when you set up the data types for your stored procedures, you need to be looking at the data types against which those parameters will be compared so that the typing matches. And you also want to do this for joins and comparisons in where clauses. So if you're joining tables on ID, for example, across two or three different tables, and those tables have ID as int, big int, tiny int, three different data types, where SQL Server will have to do the work of conversions in order to make those joins happen. And that's just extra work that doesn't need to occur. And you're actually causing a performance problem, a performance slowdown within your system when you make SQL Server do those kinds of conversions that are just really unnecessary. So think about that as you build and design tables. And for those people watching live or who will watch later, maybe you're not designing those tables, you're just querying the data. But remember that when I talked about a couple of weeks ago was one of the things I would do if I were starting over in a data career is learn the database internals for the platform I'm on, because it will help you prevent mistakes. And this is an area in which knowing the data types involved will help prevent mistakes when you're writing queries. And you can have discussions with the people at your company who are designing those tables and who have the ability or the influence to change how those tables are created. Maybe they can actually fix the data types. Knowing this database internals information, you can have those conversations about things that you notice about the data types for the tables that you're having to query in order to provide data to someone else who's asking you for information. So even though maybe this doesn't feel relevant for you as a query writer, it absolutely is very relevant. Well, I really hope that you have enjoyed this discussion about data types and understand a little bit more about how getting the right data type is actually very important in a number of ways. We hope to see you next week, and hopefully Anthony will be able to join us back at that time. We appreciate everyone who's been watching live and who has been giving us a shout out over on YouTube. Come visit the RST Ready Set Data YouTube channel. Thank you. I'm Lee Markum, Database Administrator, and this has been Ready Set Data.